Okay, welcome back. This is section 1.2 in a video lecture series on Calculus 1. And here we're going to be talking about the derivative, and we're going to be doing some very, very simple cases for the derivative and kind of exploring a older, sort of non-standard way of calculating the derivative. So the standard textbooks like Stewart, again from the intro, we're doing a slightly older approach from a Thomas Sylvanus book. It's about 75 years old, at least just by checking the publication dates and what have you. It's been updated with some new examples and some other things, but it's a very old book. And it was kind of the gold standard before Stewart. So they're going to do things maybe slightly differently. And we're going to be treating some objects in this a little bit differently than we normally would in the Stewart version of the text. So when we arrive to something where the Stewart version of the text, which is kind of how the homeworks are made, is going to do something different, I will try to point that out and just really show you the differences between the two. But I hope that this will give you just like a nice, easy way to compute a simple derivative before we get into the shortcut rules and all of the other methods for calculating derivatives like product and quotient rule. These are all going to be fairly simple things like so. So suppose that we have some function x, and we've defined some dependent variable y that is equal to that function of x, and the function is y is equal to x squared. And then suppose we want to calculate a derivative for this thing. Well, the derivatives are basically the slope. And we know that in order to compute the slope, we need to get these sort of two different points, and we need to look at what happens under kind of a small-ish increase in the independent variable, and look at how the dependent variable y responds under that small-ish increase. So under a small increase, we can write that x gets increased by this little small quantity dx. So we'll have this x plus dx squared instead of just x squared. Because it's the same function. We take a number and we square it. So here we just increase that number by a little bit and we square it. What that's going to lead us to is some small difference in y. That's because a small change in the independent variable will lead to a small change in the dependent variable as a response. So notice here that this term is like one of the binomials from college algebra, where we have several different ways of doing this. Either I can write the binomial twice and like use FOIL or something in order to expand it out into its expanded form, or maybe I can just use one of the perfect square trinomial theorems, which will give me this object if I expand the binomials. Well, notice here that in the original statement up at top, we have that this y value is just equal to the x squared value. So this thing right here that I've circled, this x squared, this is just y. If I were to take y away from both sides, then what's going to happen is it's just going to cancel out, because I've removed something that is equivalent to x squared on the right-hand side, and I've removed something that is equivalent to y on the left-hand side, because those two things are equal to each other. That's going to give me that dy is equal to 2x times dx plus dx squared. Now, recalling from section 1.1, dx squared is an infinitesimal of second order of smallness. What that means is we can just ignore this quantity because it doesn't have much of an effect on the final output. So notice here that I have dy is equal to 2x times dx, and then by simply dividing over the dx, and again there is some nuance here. This is not actually what's happening. This is not a true fraction where we can just divide over a dx, but what it amounts to is that you can do this little small move in this particular case where you divide by dx and get a dy over dx term. There will be a video at some point about the proof of what's actually happening here, but as long as you don't get like too carried away saying, oh yeah, we can always do that, and you know there's a little bit of nuance here, then you're going to be fine. You can treat it this sort of way. So let me bring this over here. We'll have dy over dx is equal to 2x. And as we might recall from the preliminary chapters in 1.1, this dy dx term is just the derivative of y with respect to x, and we see that that is equal to 2x. So the derivative of y equal to x squared is just 2x. And then we can proceed in similar fashion for other polynomial equations, and we'll always be able to produce a derivative in this fashion. I'm going to clean up the board here, and then I'll show you another example shortly. Okay, so for a second example, I've got the function of x is equal to x to the third, and I've set some dependent variable y equal to that function of x. So we have y is equal to x to the third power, and we want to find what its derivative is. Remember that the process for this is pretty straightforward. We just consider what happens to the independent variable under a small increase, an infinitesimal increase, and then we look at how that reacts with the dependent variable's infinitesimal increase. So we'll have this x plus dx to the third power is equal to y plus dy. And from here, what we want to do is, again, notice that this term here is a binomial, and it has been raised to the power of 3. So, of course, we can use our expansion theorems or any sort of method that we want, writing it 3 times and foiling it out, however you want to do it. But we just expand this binomial to the third power. That's going to give us x to the third power plus 3x to the second power times dx plus 3x times dx squared plus dx to the third power y plus dy on the left. Now notice here that we have a few things that are more complicated looking than they were in the previous case because we had a higher order equation to begin with. But if you remember in the previous problem where we did y is equal to x to the second power, we're able to ignore these terms where we have dx to the second power, dx to the third power, so on and so forth. That's because they are of second or third order of smallness, and they have very little effect over the final outcome. So anything that's been multiplied by dx to the second or dx to the third power, those are tiny, tiny, tiny infinitesimals. That means that this is an extremely small quantity. You can basically treat them as a way to wrap your head around it like it's 0. So these zeros just fall off, and I'm left with this portion of the statement right here. Basically all the way out to the first dx, and then cut everything else off. So what you have is x to the third plus 3x to the second times dx. Well, notice here that in the original statement, y is equal to x to the third. That's this guy right here. So if I take y from both sides, what's going to happen is I'm taking something that's equivalent to y off of the left-hand side, leaving me with dy, and I'm taking something that's equivalent to x to the third off of the right-hand side, leaving me with 3x squared times dx. And then the last step, same as before, if I bring this over, we just divide off the dx, and I'm left with this statement that dy over dx is equal to 3x to the second power. And it turns out that most things can actually be derived in this particular way. Most of the objects that you dealt with in college algebra, which are primarily polynomials, they can be derived in this way. And then as we go forward in the future sections and we start talking about the chain rule and the product rule and the quotient rule, which are basically the other rules of calculus that you need in order to take derivatives of more complicated functions where you have like x's on top and bottom or compositions or other things like that, all you need to know is that we can even use this nice easy method to compute a derivative to find the little pieces of the harder derivatives that we need to assemble according to some sort of rule to compute a more difficult derivative. So that is pretty much it for section 1.2. And to leave you with a note here, this is kind of like a additional homework statement, but I promise you this will make your life a lot easier. You notice each time I do this, I'm going to have to expand some sort of binomial statement, x plus dx. If you were to write out the first 5 of these, that's x plus dx to the second power, x plus dx to the third power, x plus dx to the fourth power, x plus dx to the fifth power, and x plus dx to the sixth power, and memorize what those become. You'll notice you only keep like 2 terms out of each one, because the rest of these things are all increasing order of smallness and they're basically zeros. But if you wanted to memorize those on your own time, that will make your life a heck of a lot easier when you try to do the homeworks that will be assigned in class.